Okay, this is going to be the lesson video for Calculus 3, section 13.4, which is velocity, acceleration, and projectile motion. So let me go ahead and share the notes here, and I'll go through the presentation. All right. So here we're going to talk a little bit more about applications now that we've talked about various things related to the vectors. Let's go ahead and just define velocity and acceleration based on things that we've seen in previous calculus classes. So even back to brief calculus, we were talking about the fact that if you just have a function in 2 dimensions that just shows distance in a single direction, which we would usually call displacement s, as a function of time, like let's say we had s is t squared minus 5t plus 8 meters away from some origin, right? Then that traces out some sort of a curve, right? The distance versus time, right? And then we said that if you had 2 places on the curve, like a starting point and an ending point, you could find the average speed to go that distance in that amount of time. Just take the difference in the distance divided by the difference in the times, and that gives you this this difference quotient structure, right? So if you had a time t, and then you want a time t plus h away from that, and then you had the distance at that point was the distance function at t plus h, and then minus the distance function at t. That's a change in y over a change in x, which is a slope, and that gives you what we called back in brief calculus the average velocity, right? But then if you want the instantaneous velocity, we called it velocity, but really it's speed, which we'll define more crisply here in a second, right at this value t, then you had to bring these points closer and closer and closer together by taking the limit as h approaches 0, and then that was our definition of the derivative. So we derived that the velocity is the derivative of the distance, right? So to go from a distance equation to a velocity, you take the derivative, right? And then so we can actually have an expression that would allow us to plug in different times and find the instantaneous speed at each of those times, right? And then we further said that if you take the derivative of the velocity, you get acceleration, because that's how fast velocity is changing, okay? And so if the displacement or distance was in meters and the time was in seconds, then velocity would be meters per second, and acceleration would be meters per second, or meters per second squared. Okay, so that's just in a single dimension, right? But in this class now, we can have motion in 3 dimensions, right? So instead of displacement, we're going to define position using our old friend, the position vector, r. So r as a function of a parameter t is going to be the position that shows the position to a point at any time. And now our parameter t is for time, and we can kind of see why we typically parameterize using t. The book likes to do this because so frequently time is the thing you're varying. So it's still a parameterization of the spatial curve. And so position vector is our displacement. The derivative of that would be velocity, and then the derivative of that would be acceleration. But then in this case, all these things are vectors. So that means you're going to take the derivative of the x, the derivative of the y, and the derivative of the z separately. But you can kind of consider it one operation. So the idea is to go from position to velocity, you take derivatives, right? And then to go to acceleration, you get derivatives. And then in each case, though, you get a vector which shows the direction of these things as well. And then if you had to go the other way, let's say that you had the acceleration, you want to go back to the velocity, you'll take the integral, right, with respect to time. And then same thing here, you take the integral with respect to time to go backwards, okay? All right, so we'll see some examples of that, and it will become more clear as we get to specifics. Okay, here's a first example. Let's say that we have a position vector given by 3 cosine t, 2 sine t, and t, and we want to evaluate the position, velocity, and acceleration at time t is pi over 3. Okay, so we start with the position vector, and then we would just say, all right, the velocity vector is just the derivative of that. So the way we take a derivative of a vector, is we just take the derivative of each part separately. So the derivative of cosine is negative sine, so this is going to be negative 3 sine t. The derivative of sine is cosine, so that's 2 cosine t, and then the derivative of t is 1, right? And then to get the acceleration vector, that's going to be, so the velocity is the derivative of the acceleration, the derivative of the position, and the acceleration is the derivative of velocity. And so we'll just do that with the vector. So the derivative of this, derivative of sine is cosine. This would be negative 3 cosine t. And then the derivative of cosine is negative sine, so negative 2 sine of t, and the derivative of 1 is 0. Okay, and then you could find the particular values for position, velocity, or acceleration at any given time or any given parameter value. So you just plug the parameter values in. So for that, right, we could say, all right, so the position this is a vector, the position at pi over 3 is going to be 3 times the cosine of pi over 3, 2 times the sine of pi over 3, pi over 3, okay? All right, so just using a unit circle, this is one of our special angles, pi over 3, where we have 1/2 for the cosine and square root of 3 over 2 for the sine. So this is just going to be, let's see, the cosine is 1/2, so this is just 3/2 in the x direction. 2 square root of 3 over 2 would be square root of 3, and then pi over 3. And then we can do the same thing for the velocity and the acceleration vectors, right? That means that you could say, okay, the velocity at the place where the parameter is pi over 3 is negative 3 times the sine this time of pi over 3, 2 times the cosine of pi over 3, and then 1. And so this would be negative 3, and let's see, the sine of pi over 3 is the square root, so that's going to be negative 3 square root of 3 over 2, and then this is going to be 1/2, so this is going to be 2 times 1/2 is 1, and then 1. So that gives me not only how fast the particle or object is moving, but also its direction. And then for the acceleration vector evaluated at pi over 3, right, would be negative 3, and then the cosine of pi over 3 is 1/2, so that's negative 3 over 1/2. And then this would be negative 2 times the square root of 3 over 2, so negative square root of 3 and 0. So this gives me an acceleration vector, okay? So we can find a position vector, a velocity vector, and an acceleration vector at any particular value of the parameter, which in this case is time. All right, so as far as what that means, if you were to take this position curve and use some sort of nice 3D graphing software like this GeoGebra program here, it would show that this is a helix, right? It's an elliptical helix, right? We know because we have a cosine sine for x and y. So in the x and y plane, it's tracing out a curve that's circular, but wider in the x direction. So it's an elliptical helix, and then t is just, the z is steadily going up. So elliptical helical path like that. Right, so if you were to plot these position vectors, velocity vector and acceleration vector at the time pi over 3 for the parameter, you get something like this, right? So our position vector, I'm going to use red to highlight here, our position vector is from the origin to that point at that time, right? That's r. And then the velocity vector happens to be this way, right? This is the v vector, right? And it's perpendicular to this r vector, right? Because, well, not necessarily, but in this case it is, because this is roughly circular motion, so almost perpendicular. But what it shows is, as the object is moving along its path, this is not only the speed, but the direction of motion at that instant, right? And then, interestingly, this third vector, the acceleration vector back here, we're going to find shows what force is acting on this particle at this point to cause it to be changing its velocity in this way. Okay, so the position vector gives the position of the point in space. The velocity gives the speed and also the direction that it's moving at that instant. And then the acceleration is related to the force that's acting on the point to cause the change in velocity. All right. So we'll define speed now specifically as the magnitude of the velocity vector. I think we imprecisely back in brief calculus called the speed the velocity, but now we know velocity is actually a vector because it has a direction as well as length. And we're going to define the word speed to be the magnitude of the velocity, right? And then that would be in units like, say, meters per second, something like that. And then the acceleration is the rate of change of the velocity vector. So an acceleration is anything which causes a change in velocity, okay? And that means that the speed doesn't have to change. If even the direction of the velocity is changing, that means an acceleration has been imparted on that, right? This is related to Newton's second law of motion, F equals ma, right? Acceleration is a force divided by mass, whereas a proportionality constant, the larger the force, the larger acceleration, right? And so what that means is, like, let's say you had circular motion, like imagine a ball that was connected to a string and we were twirling the ball around in this direction like this, okay? Well, even if we're twirling at a constant speed, so the speed of the ball is not changing, right? At this instant, the velocity vector is in this direction, right? But then at a later instant, the velocity vector is in this direction. So even though its speed hasn't changed, the magnitude, since the direction has changed, that means an acceleration is being implied, right? And these blue acceleration vectors show the acceleration vector. In fact, the acceleration vector points back towards or in the direction of the force that's causing that acceleration. So in this case, the force is being, imparted by the person that's holding the string here. And so the force is towards the center of rotation like that. And that's an acceleration that way, right? So acceleration defined as a vector allows us to analyze forces that are not necessarily causing change in speed, but are causing changes in the direction, in the velocity vector's direction. All right. So projectile motion is a special case of motion, right? And really it comes down to this. If an object is only being acted on by gravity, that's the only force. Like maybe we launch it in some way, right? We have some initial force, impact or something, impulse, right? But once it's in motion, the only force acting on it is gravity. Then this is called projectile motion, okay? And in general, when we analyze, we start with a vector for acceleration because that's the thing that's constant. So you're going to have something like maybe in 3 dimensions, you have a position, maybe some initial position vector to a starting point. You have an initial velocity where this is maybe like a cannonball that's being launched, right? But then from then on, the only thing that's acting on the force is gravity. Typically, we would use the negative z direction, or if we were in x, y, 2 dimensions only, the negative y direction. And so that means the acceleration would have a vector that has 0 in the x and y, and then some gravitational constant acceleration in the negative z direction. Okay, so remember we said that if you wanted to go from position to velocity to acceleration, you take derivatives. If you need to go the other direction, you take antiderivatives, so you take integrals. So to go from acceleration back to velocity, we're going to take the antiderivative of that acceleration vector, okay? And so the antiderivative of a vector is you take the antiderivative of the x, y, and z components separately, right? So this still stays z at 0 and 0, but this negative g constant becomes negative gt, plus there's always an integration constant, right? But this time that constant is a vector, okay? And so what you have to do to establish this is you have to have a particular value for the function at a given t, plug that t in here, and then solve for the constant. And very typically, the t that's given is 0, which very frequently makes this vector 0. So this integration constant is often the initial velocity vector. So the x, y, and z components of the initial velocity, right? And so you'll typically have the initial velocity in the x and y direction and z, and then the acceleration caused a change just in the z component only of the velocity. And then to go from velocity to position, you do the antiderivative again. So you take the antiderivative of that. It also has an integration constant, but that one typically is related to the initial position vector. Okay, best to see this when we go through a specific example, but this shows that this could be true in 3 dimensions. Okay, and so what you typically get is something like this, a very simple acceleration vector that gets more complicated with velocity when we account for the initial position, or initial velocity, and then the position vector is more complicated still. But in every case, to go from one step to another, we're taking the antiderivative with respect to time, okay? And then at the end, right, the typical kind of trajectory, sometimes this will be called the trajectory, which is the path, the space curve that the object takes through space. It has its initial position, and then plus however long it's been traveling times its initial velocity. Nothing can change that. The initial velocity is imparted and is there throughout the problem. But then there's this extra term out here that came from the gravity operating on it. And since the gravity is in the negative direction, it actually usually only affects the z term. Okay, To keep things more manageable, a lot of times we're going to do the projectile motion problems in 2 dimensions only. So we'll just remove one from consideration, and in that case, we'll use x to the left, y to the right, and the gravity will be in the negative y direction like this. So we'll start with an acceleration vector like that, right? And then when we have typically an initial velocity vector, it's then easy, as long as we know this angle of elevation here, it's very easy to figure out the x and y components, because it's just the magnitude of the initial velocity, the speed, times the cosine of that angle in the x direction, and then the magnitude times the sine in the y direction, okay? All right, so rather than kind of go through and explain all of this, let me just work a problem. I think that'll make it clear when we just work a problem. So units, all right, so for units, distance is in either feet or meters, velocities in feet per squared or meters per second, feet per second or meters per second. Acceleration is feet per second squared, meters per second squared. Mass is in either slugs or kilograms. Forces are in pounds or newtons. And then the gravitational constant, you can use 32 or 9.8 or 9.81. All right, let's do a problem. This is where we really kind of see how it works. And this is very, very similar to the way this is assessed on the chapter test. So let's say we wanted to find position and velocity and position vectors for a particle that has a given acceleration and then the given initial position and velocity. Now this one is actually not projectile motion because we don't have acceleration that's only gravity, right? They're telling us actually that the acceleration is changing over time. Okay, so this is the most general problem we could see, right? This would have to be something where the particle itself is accelerating, you know, besides gravity, like maybe a rocket ship whose acceleration is changing over time because the mass of the propellant is being released or something like that. But anyway, we start with acceleration. That's the starting point. We somehow come up with an acceleration. In this case, they gave it to me. In projectile motion, typically this would be 0, 0, and then negative g. Okay, but they gave it to me here. So to get velocity, the velocity as a function of the parameter t is going to be the antiderivative of the acceleration vector. Okay, so all I'm going to do here is take the antiderivative of each term with respect to the parameter t. So this 2 becomes a 2t, and this, if I raise by 2, this is going to be 3t squared, right? The antiderivative. And then this would be negative 4t cubed. So I just did the antiderivative really quickly, right? And then, but there is an integration constant, okay? So this integration constant, we have to have a value to plug in to evaluate. Now, luckily, they gave me this, that the velocity when t is 0 is this. So if I plug 0 in for t here, I get 0, 0, 0 plus that integration constant, which is really a vector. That has to equal the vector 1, 0, 0. And so that means that the integration constant vector is simply this 1, 0, 0, right? And what that means is that the true complete velocity vector is the velocity vector versus time plus the constants here. So the x is 2t plus the initial velocity of 1. And this is 3t squared plus the initial velocity of 0. And then this is the negative 4t cubed plus the initial velocity of 0. So I added this into this vector. That's so I basically used an initial condition to establish the integration constant's value. Okay, now to get the position vector, so that would be the answer to the velocity vector. That's the velocity vector. Okay. To get the position vector, I know that that is the antiderivative of velocity. Since velocity is the derivative of distance, distance is the antiderivative of velocity. And so I'm going to take the antiderivative of this. I'll do each term separately or each component separately. So this would be t squared plus t, right? For the y component, we're going to have t cubed. And then here, this is going to be negative t to the 4th. Is that right? Yep. Plus, again, an integration constant. Okay, so for me to establish this, I need to know what is the position vector at some value for t. Well, and they gave me another one, happened to do 0 again, which makes it easy because if I plug 0 here, I get 0, 0, 0, plus this integration constant equals the position vector 0, 1, negative 1. And so that means that this integration constant vector this time is 0, 1, negative 1. And that means that the position vector is t squared plus t plus 0, and then t cubed plus 1, and then negative t to the fourth minus 1. This would give me the true position that builds in the effective acceleration, the effect of the initial velocity, and the effect of the initial position. So that's the general pattern. We just do antiderivatives as we go from acceleration to velocity and velocity to position. All right. Okay. And in the case of projectile motion, usually you would have some acceleration function that looked more like this, like the acceleration would just be negative 32 in the, so it'd be like the gravitational constant, but in the negative direction. If it was 2 dimensions, or if it was 3, this would be in the z direction. Not this problem, but for projectile motion, typically we have a simpler acceleration, which means this work is even simpler. All right, so that's it for the lesson. When you try the homework, let me give you a couple of hints for that. On number 19, we're trying to find the expression for speed, but it's the maximum speed, if I recall. And so remember that once we have an equation for speed, you can maximize anything or minimize anything, or it looks like this is asking us for minimizing, whenever the first derivative of that is 0. So you can use the fact from earlier in calculus that optimum points occur when the derivative is 0. For number 22, I believe we're trying to show that the t and n vectors are always orthogonal, right? And so to make it more manageable, what you could do is you could just consider a helical path as an example, maybe, and then use the parameterization that r is cosine t sine t, and then just verify that this is true because the dot product is 0 when you go through and find the t and v vectors, right? If you really, really want to challenge yourself, you can prove this is true in all cases, but to do that, you have to have a general expression for r, right? So what you could do is you could use this structure. So just take a look at this structure and say that there's some velocity vector that has a magnitude, and you can use the direction angles, alpha and beta, and show that these projections give this in the directions here, right? So just you can verify this picture and then go through the process of finding t and n and show that even in this general case that those will always be orthogonal by checking the cross product or the dot product being 0. You don't have to do that unless you want to challenge yourself. You can just pick an example case like a helical path. I mean, that's not really proving, but it's demonstrating that it's true for a family of curves. So that'd be fine. And then for number 29, you're trying to breach or lob a cannonball into a fortress that has 500 meters between walls, because that's the length of some of the sides, right? We're 100 meters away from one edge of the fortress, and then the walls are 15 meters high. So you're really trying to find the angles, the two angles of elevation that would allow you to lob this in. So if you look at the kind of picture of the problem, you can use this picture, right? In one case, you're going to lob it really high so that it barely clears the first wall, right? So think of it as having to pass through this point, right? And then the other one is you can lob it in such a way that it barely hits this wall and bounces back in. So you can think of it as trying to patch through this point. So give that a try. If you're on the right track, you'll end up getting a quadratic that involves tangent of the angle, okay? And so you can use this trig identity, secant squared is tangent squared plus 1, to solve. So if you seem like you're going off in the weeds, but you end up with a tangent, try this and see if you can finish the problem. And of course, we'll probably go over this one in class. Or you can ask me in tutoring if you're watching this some other time. All right, that's all I have for you for 13.4.